Okay, so 2.34 gives us a step potential where V is equal to 0 everywhere to the left, and it's equal to some positive constant everywhere to the right. And in part A, we're asked to calculate the reflection coefficient in the case where the energy is less than V naught for a free particle, and comment on this answer. So immediately, we should see that there's basically just two different sets of Schrodinger equations here. To the left, we have d2 psi by dx squared is equal to negative 2me divided by h bar squared times psi, and we've done this many times before over the course of this chapter. This is just the free particle solution, a e to the ikx plus b e to the negative ikx, where k is going to equal the square root of 2me divided by h bar. Similarly, on the region to the right, so let's label this x as less than 0. So on the region to the right where x is greater than 0, we have d2 psi by dx squared being equal to 2m over h bar squared times v naught minus e multiplied by psi instead. So this is going to equal L times psi, where L is going to equal the square root of 2m v naught minus e divided by h bar, and we've done this many times as well in the earlier sections. This just gives us a generic exponential function, f e to the lx plus g e to the negative lx. Immediately we see, so a e to the ikx plus b e to the negative ikx doesn't blow up ever. However, on this side, x is going to positive infinity, and if we don't let f equal to 0, then f e to the lx is going to blow up. That's going to give us an invalid wave function, so automatically we require that f is equal to 0. Our resulting piecewise is going to look like a e to the ikx plus b e to the negative ikx when x is negative, and g e to the negative lx when x is positive. So at this point, we want the reflection coefficient, which is going to require us to find the ratio of b over a. To do that, we have to start by solving the system of equations. So immediately we have continuity of psi at x equals 0, which is just going to give us that a plus b is equal to g, since all of the exponentials disappear at x equals 0. Next, we have continuity of the derivative, which is going to give us ik times a minus b is equal to negative lg, where I take in the derivative of each of these functions, and I once again plug in x equal to 0, and that gives me this. Next, we can sort of combine these, and we get, plug g into here, we get ik a minus b is equal to negative L times A plus B. If I want to move the L over, I get IK over L times A minus B is equal to negative A minus B. Move all the A's to one side, move all the B's to the other, I get IK over L times A plus A is equal to IK over L times B minus B, otherwise defined as IK plus L over L is equal to B times IK minus L over L, where I'm separating this into IK over L minus 1 and IK over L plus 1 respectively. Next, recognize that reflection coefficient is the magnitude squared of B over A. So we start by getting B over A. B over A is going to equal IK plus L over L multiplied by, move this over to that side, and that's going to give us L over IK minus L. And this is going to result in IK plus L over IK minus L. If we then take the magnitude squared of this and recognize, that this is actually equal to L plus IK over negative L plus IK. If we then take the magnitude squared of B over A, we can recognize that these are both complex functions, and taking the magnitude squared of a complex results in, A squared plus B squared. So this is just going to equal L squared plus K squared over L squared plus K squared, which is then going to equal 1. So therefore the particle has a 100% chance of reflecting and will never ever make it through this barrier, which makes sense because remember, this is effectively a bound state to the right, because the potential is always going to be greater than the energy all the way up to positive infinity. So there's no chance that the particle can ever burrow through it, because it's never going to get through it, because there's always going to be a barrier all the way to positive infinity. Okay, So in part B, we're asked to do the exact same thing, except now E is greater than V naught. So what we have now is that the energy is always bigger than this barrier. This is effectively just a free particle, but we have two different floors, one to the negative side and one to the positive side. So the way we solve it is we solve it like a free particle, except we have two different sort of constants here. When x is less than 0, we use k, where k is equal to the square root of 2me over h bar. And then when x is greater than 0, we use L, where L is going to be E minus V. You're going to have this E minus V naught instead of an E term. So for reference, K is equal to the square root of 2me divided by h bar. And L is equal to the square root of 2me minus V naught divided by h bar. So immediately, the resulting wave function we have is psi is equal to, and then on the left we have a e to the ikx, plus b e to the negative ikx, and on the right we have f e to the ilx plus g e to the negative ilx. And we do the same thing we always do for free particle systems, which is we assume that our particle is incident from the left side. So because of that, this g term never ever appears. G therefore equals 0 by default, and we have this. Now, if we want the reflection coefficient, we have to apply boundary conditions. So continuity of psi is going to give us that a plus b is equal to f, and continuity of the derivative of psi is going to give us that ik times a minus b is going to equal il times f. So then if we plug these in, if we plug f into here, then we get k times a minus b is going to equal L times a plus b, or k over L times a minus b is equal to a plus b. So at this point, getting like terms in, we get k over L times a minus a is equal to k over L times b plus b, or a times k minus L over L is equal to b times k plus L over L. And at this point, realizing that the reflection coefficient is the magnitude squared of b over a, then we get that b over a is going to equal k minus L over L times L over k plus L, which is going to equal just k minus L over k plus L. Therefore, the magnitude squared, and therefore the reflection coefficient, is going to equal this thing squared, which is going to be k squared minus 2kl plus L squared over k squared plus 2kl plus L squared. And now we want to express everything in terms of the actual proper variables. We're going to copy paste these definitions for k and L and move them over here. And we're going to do some simplification here. So k squared is going to equal 2me over h bar squared. 2kl is going to equal, let's see, 2 times, and then 2m square root e times e minus v naught divided by h bar squared. And then finally L squared is equal to 2m e minus v naught over h bar squared. And immediately what we see is that every single term in this reflection coefficient shares a 2m over h bar squared. So we can just get rid of that and just basically move it out. So finally r is going to equal e squared minus 2 times the square root of e times e minus v naught, and then plus L squared, which is going to be plus 2m, or sorry, no, the 2m gets factored out, so e minus v naught. And this isn't supposed to be e squared, it's e. Apologies. And then at the bottom we have the same thing, so k squared is going to give us e plus 2 times square root of e times e minus v naught, and then plus e minus v naught. Combining like terms, we get that we have 2e minus v naught minus 2 square root of e times e minus v naught. And then at the bottom we get 2e minus v naught plus 2 square root of e times e minus v naught. And that is our answer. Okay, so in part C, were said that for a potential such as this one that doesn't actually go back to 0 to the right of the barrier, the transmission coefficient isn't simply just the magnitude squared of the ratios of f over a, and the reason why is because the transmitted wave travels at a different speed. So to give a little bit of insight of what this actually means, let's just consider a standard finite well, or finite barrier, I suppose. So let's say our barrier is this high, and then let's say our incoming particle has an energy E that's less than the barrier. So, when we do this, there's going to be an instant wave, ae to the ikx, and then a reflected wave, be to the negative ikx. In the middle here, we're going to have some garbage that we don't care about if we're looking at transmission and coefficient and reflection coefficients. Like, they do matter, but ultimately they're only used to solve the system of equations. They don't actually play a role in the final results. And then finally, we have f e to the ikx for the outcoming wave. And if we want to find the transmission and reflection coefficients, we take respectively the magnitude squared of the ratios of fa and b together. So the thing about this is that this sort of assumes that the potential drops to 0 infinitely far away, and if that happens, then ultimately the transmission coefficient, which is the ratio of f over a and taking the magnitude squared of, these both involve waves in the same medium. Same thing with the reflection coefficient. A and b both involve waves in the same medium and by the same medium I mean in the region where v equals to 0. In contrast, for something like this where the potential just goes to non-zero infinitely far away, what this physically represents is that at x equals 0 there is a wall, and this wave is propagating through the initial medium, which has a potential of 0, going into this new medium, which has some positive potential v naught. So in real life, the only way that this is possible is basically just a wall that goes infinitely far away to infinity. So this effectively is a different medium in physical terms. It's a different medium for the wave to go through, and therefore, since it's a different medium with different properties, it has a different wave speed as it goes through this medium. So the problem is that this calculation does not assume that the medium is different. It sort of intrinsically assumes that the speed is always going to be the same, because if you remember, the actual separable solution, psi of x comma t, is defined as psi of x times phi of t. And all of the information that's included in the speed of the wave is included in phi of t, because this gives us something like e to the vt. And, because the full solution is e to the ikx plus minus vt. So the speed is intrinsically included in phi, which isn't sort of part of our calculations because we have always been doing everything via psi. So because of that, this sort of problem, or this method, sort of doesn't actually work properly for our step well where v is not going to 0 infinitely far away. So we want to show that instead there's this extra factor of the square root of e minus v naught over e in front of it for e is greater than v naught. And we're told to use the probability current. So for reference, we calculated the probability current back in chapter 1, I believe, and it was that the probability current for a wave function was defined as I h bar over 2m times psi d psi star by dx minus psi star d psi by dx. And by probability current, we mean, how much of the probability density is moving in a given direction over time. So the primary difference here is that the probability current actually includes the speed of the wave intrinsically via the term current, which sort of implies a measurement of how fast the probability is moving, because once again, current is defined as how much of something is going through an area per unit time, which sort of intrinsically implies speed. In contrast to that, solving the system as before using these coefficients a, b, and f doesn't take into account this speed. So we have to do it this way via probability current. So for reference, our wave function in part B was defined as a e to the ikx plus b times e to the negative ikx when x is less than 0, and then finally f e to the I lx when x is greater than 0. And what this actually is this is 3 separate wave functions, but just implied with superposition on top of each other. So what happens is that the incident wave, psi incident, is equal to a e to the ikx. The reflected wave, psi r, is equal to b times e to the negative ikx. And the transmitted wave, psi t, is equal to f e to the I lx. And what happens is that all of these waves, if you've taken, classical mechanics, I believe, you should know that waves will superimpose upon each other, and quantum waves are no different. So because of that, the actual net wavelength of the system is going to end up being the superposition of all of these functions together. And from there, what we can say is that, okay, we can calculate, the probability current for the incident wave and the transmitted wave. So J incident is going to equal I h bar over 2m times a e to the I kx times the derivative of the complex coefficient. So let's see, let's also just write the complex coefficient. I star is equal to a e to the negative I kx, and psi t star is equal to f e to the negative I lx. So this is going to be multiplied by d psi star by dx. So this is going to be negative a I k e to the negative I kx, and then subtracted by a e to the negative I kx multiplied by the derivative of psi, which is going to be a I k e to the I kx. And if we multiply this out fully, we get, let's see, negative a squared I k, and then the exponentials cancel, subtracted by a squared I k. Once again, the exponentials cancel. This is going to be I h bar over 2m times negative 2a squared I k. The i's cancel and make a positive, so this is going to be h bar over m. The 2 cancels, so the 2's cancel, the i's cancel with the negative here, and we're left with h bar over m a squared times k. And then similarly, jt, transmission probability, is going to equal, let's see, I h bar over 2m multiplied by f e to the I lx multiplied by negative f I l e to the negative I lx minus psi star, which is going to be f e to the negative I lx times the derivative of psi, which is going to be f I l e to the I lx. Doing the same thing, this is going to give us I h bar over 2m times negative f squared I l minus f squared I l, or I h bar over m times negative f squared I l. The i's cancel out like this. This is going to give us h bar over m f squared l. And next, what we can recognize is that probability current in units is just probability per second. So sort of dividing them gives a relative probability in the exact same way that dividing normal probabilities will do. So if we do that, right, because current is equal to, however much of something passes through a given area per second. So current is proportional to like units per second. So probability current is going to be like probability per second. So if we divide one probability by the other, we're going to get the relative probability. And just to flesh this out, j t divided by j I is going to equal, t units per second times second per I units. And this is just going to be, probability of t divided by probability of I, which is going to be the relative probability. So if we do this, then what we're going to get is that jf divided by ja is going to be equal to, if we look, or sorry, not ji. So if we do ji, then what we're going to get is we start with jf. This is going to be h bar over m times f squared times l. And then we're multiplying by the reciprocal of ji, which is going to be m over h bar times 1 over a squared times k. If we recognize that f and a can be sort of complex numbers, these squared terms are actually, in fact, magnitude squared terms. So this is going to be L over K times magnitude F over A squared. And if we remember what L and K are, this is going to be equal to the square root of 2m times E minus V naught, all divided by H bar, multiplied by the reciprocal of K, which is going to be H bar over the square root of 2me, multiplied by F over A magnitude squared, and this is going to equal, the 2m's cancel the square root of E minus V naught over E multiplied by the magnitude of F over A squared. And with that, we have our answer, and we are also done with part 3. Apologies, I realized I forgot to do the final part of problem C, which is what is T for the other case where E is less than V naught. This is kind of trivial because if we look at E is less than V naught earlier, we found that the reflection coefficient was just 1. There's no chance for the particle to propagate through this medium if V goes all the way, always greater than E to infinity, because remember, this is just a bound state, in this case to the right. This remains the same. It's the same scenario even after including this new fact, because once again, the transmission constant, if it's 0 initially, it's still going to be 0. If magnitude F over A squared is 0 initially, adding this extra factor at the front doesn't really do anything. So in the case where E is less than V naught, it's still, transmission coefficient is still equal to 0. Okay, so for the final part of this problem, we want to calculate the transmission coefficient for the E greater than V naught case, and we want to verify that T plus R does in fact equal 1. So for reference, we have the boundary conditions via the continuity of sine, the continuity of its derivative here, and we also have our new expression for the transmission coefficient in the case where the potential does not go to 0 and infinitely far away. So at this point, it's just a matter of solving this. So immediately, I can say, okay, B is equal to F minus A. Plug that in down here, I get IK, A minus B is equal to ILF, or whoops, sorry, I forgot to replace the B. We get IK, A minus F plus A is equal to IL times F. Get rid of the I's, we get K times 2A minus F is equal to LF, or 2AK is equal to F times L plus K. Or modifying this again, we get that because we want F over A, so 2K over L plus K is going to equal F over A. So at this point, T, there's no complex numbers here, so T is just going to equal, so the square root of E minus V naught over E times 2K over K plus L squared. So calculating this out, we get that T is equal to the square root of E minus V naught over E multiplied by 4K squared over K squared plus 2KL plus L squared. Remembering that K is equal to the square root of 2ME divided by H bar, and L is equal to the square root of 2M times E minus V naught divided by H bar. Multiply these out, we get that T is equal to the square root of E minus V naught over E, and then our big fraction, so this is going to be, let's see, 4 times 2ME over H bar squared, and then divided by K squared, which is 2ME over H bar squared, plus 2 times KL, so this is going to be 2m times the square root of E times E minus V naught, and then we're dividing this by H bar squared, and then we're adding L squared, which is going to be 2m E minus V naught over H bar squared. Close this off. Everything has an H bar squared term. We can cancel that out. This is equal to square root of E minus V naught over E, and then our new fraction. So let's cancel out all the H bar squares. We can also cancel out all the 2m's. And we're left with is 4e divided by, let's see, e plus 2 times the square root of e times e minus v naught. And then added with e minus v naught. Combining the two e's, we get square root of e minus v naught over e multiplied by 2e minus v naught plus 2 square root of e minus v naught, all divided under 4e. So at this point, we want to prove that this added with r does in fact equal 1. So if we do that right here, recognize that r is equal to this, t is equal to this, t is equal to this. So we're trying to add these together. And let's see. Immediately, I see that the denominators are already the same. So for convenience, I don't want to multiply this factor onto the denominator. I want to multiply it onto the top. So what I get is that t plus r is now equal to, let's see, 2e minus v naught minus 2 square root of e times e minus v naught plus 4e times the square root of e minus v naught over e. And then all of this divided by 2e minus v naught plus 2 square root of e times e minus v naught. So let's see. This is plus 4e. I can combine these, and what will this give me? If I move this in, this can get turned. So this 4e, I can move the e into the square root, and this is going to give me 4 times the square root of e times e minus v naught, because the e becomes e squared, multiply by the e at the bottom, cancels out the e at the bottom, leaves the e at the top. 4 and then minus 2 square root of e times e minus v naught, that's just plus 2. So this is going to equal 2e minus v naught plus 2 times square root of e times e minus v naught at the top, and then at the bottom we have 2e minus v naught plus 2 square root of e times e minus v naught. Let me just double check that this is in fact correct. 2, yes, okay, and this is just equal to 1, so therefore our transmission and reflection coefficients do indeed equal 1, and we are done with this problem.